Welcome back. So now we're going to be talking about how to use the formula that we derived in the optional video. So don't worry about how we got to it. These two big boxes here have the two formulas that we're going to use. Okay. Use the wrong marker here. So this big box on the top just talks about how to compare the object distance and the image distance to the focal length as well. And the one on the bottom here talks about finding the magnification. So M is your magnification. Yeah. Now, a few things about the magnification number, because it is a number that we can find, because it's just a comparison between the HI and the HO here. So I can compare those two things. I just divide them. If the HI is larger than the HO, which means the image is larger, so that means if the I'm going to do it absolute values. If this is greater than 1, then we have an enlarged image. If the absolute value is less than 1, which just happens to be greater than 0 because it is absolute valued, if it's less than 1, then we have a diminished image. Okay? Now let's get rid of the absolute values and just talk about if it's positive or negative. So if this ends up being a negative number, then we have an inverted image, so it's upside down. And if it ends up being a positive number, then we have an erect image, which sometimes we say is upright. Okay. So the magnification helps us determine a lot of things about the characteristics of the image. The DIs and the DOs can help us figure out a couple other things as well to determine if it's real or virtual image. So to determine certain things about using the formula to determine characteristics about the image, we need some other sign conventions. The magnification, depending on what sign the magnification tells us what kind of image it could be or what kind of attitude it is. Is it erect or is it inverted? But to use the equation properly, we're going to have to deal with a few other sign conventions. So when we're dealing with the distances, like DIs and DOs, if the distance ends up being positive, then that's what we call a real image or a real object. And the thing is, real objects are always real, right? So object distances, so DOs, is always going to be a positive number. This is always going to happen. So you never have a negative DO, okay? Your DI could be negative, it could be positive. If it ends up being positive, it's a real. If it ends up being negative, there's no such thing as a virtual object. Okay, I'm just going to get rid of that piece. If you have a virtual image, we have a negative DI. So this would be my DI would be less than 0. And my DI up here, my DI would be greater than 0. Okay, erect images have a positive height, so my HI would be a positive number. Inverted ones, my HI would be a negative number. Now my object's height will always be positive, no matter what. So my object height is always positive. Just as if it's always a real image, we always consider the object height to be positive because you're just comparing, I want to compare the two. So I don't care if my object's upside down, the image is inverted if it's just the other way. So just treat your object, even if it's upside down, to be positive, so we know what sign it comes out as the image, if it's inverted or positive. Now, the two types of mirrors we talked about are concave mirrors. A concave mirror has a focal length that is a positive number, and a convex have a focal length that is a negative number. You can think of this logically about where is the focal length in this here. The focal length is on the same side as the observer. So it's on this side. So I'm here, I'm looking at the mirror. That's where the focal length is on the same side. Now on this one here, the focal point is somewhere back here because this is the circle here. The center of the circle is out here somewhere. I'm on this side, but the focal point's on this side, so that'd be a negative focal point. And having those positive and negatives makes the math work. Right? If you don't use the positives and negatives properly, you're not going to get the proper answers. Okay, so let's see how this works. I think I have about 4 or so questions. Let's see how this works for some of these questions here. Okay, so an object is located 20 centimeters from a concave mirror. So that's good to know. It's a concave mirror. Okay, that has a focal length of 15 centimeters. Where will the image form relative to the mirror? So looking for the DI here. So just put that here, my DI question mark. And the second question is, if it has a specific height, what is the attitude, height, and the magnification of the image? Okay, so let's go through and list off what we have for question A here. So question A, we have an object that's located 20 centimeters from the concave mirror. Okay, it's a concave mirror, so that means this is a positive focal length of 15 centimeters. A little bit of positive there. Just to emphasize, this is concave, it's a positive number. My DO is also a positive number. It's always going to be a positive number. I'll just put that there too. So I'm going to use the formula 1 over F is equal to 1 over di plus 1 over do. I think it says do over die. Okay, yeah, it doesn't really matter. I'm going to be looking for di in this first one. Now to use this formula, the best thing to do is to rearrange for 1 over di. So I want to get 1 over di by itself, so I'm going to subtract over the 1 over do. So 1 over f minus 1 over do. I'm going to put in my numbers first. So I'm going to go 1 over 15 centimeters. Now, if you leave the units in centimeters, because there's no constants here, no like Coulomb's constant or gravitational constants. They're not forcing you to keep the units in a very specific way, but they have to be the same. So I have centimeters, the other one has to be centimeters. I can't mix them up. If I use centimeters, I get centimeters out. And then I'm going to go minus 1 over do. So you might get a minus minus situation sometimes in these kinds of questions. So you have to be very careful, but this one's just a plus 20 at the bottom. Okay, so I'm going to punch this in my calculator. 1 over 15 minus 1 over 20. I'm going to go math enter. I'm going to get 1 over 60 as my answer. 1 over di. 1 over di is equal to 1 over 60. Now, to get the di by itself, now you flip this over. So you could times the di up to the side, you could times the 60, or you can take it because it's just a fraction equal to a fraction. Take those two fractions and flip them over. So this ends up being 60 over 1, or 60 centimeters. Now it ends up being positive. That's going to be very important later on. Because this is positive, because it ended up being a positive number, this is considered a real image. So what is the type of the image? It's real. Okay. For B, we're going to use the other formula for magnification to help us figure this out, because it wants the magnification of the image, what's the attitude, it wants the height. So I'm going to use M, so you go to HI over HO, so you go to negative DI over DO. Okay. So we have the object's 5 centimeters, we have the DI, we have the DO now. So I can put all these numbers in here. So first of all, I'm going to solve for M. So M is equal to negative DI over DO. I just ignore the height part for now. So negative 60 over 20, positive 20. So I get negative 3. Okay, so this is telling me a few things. No units here because it's centimeters over centimeters, so those cancel out anyway. This is telling me a few things. This is telling me that this is inverted because it's a negative number. It's telling me that it's enlarged because the absolute value, is greater than 1. So it's enlarged. Okay. It doesn't tell me the height of the image, so I'm going to use this negative 3 now. In this part of the formula, HI over HO. I just rearrange this for HI. So negative 3 times HO. Negative 3 times, I think it said 5 centimeters there. Yeah. 5 centimeters. So I get a height of negative 15 centimeters. Again, got negative height, so that just confirms that this is inverted. It's much larger. It's 15 versus the 5. So it's enlarged. There you go. I think that's all we wanted to figure out. Yeah, looking good. Cool. So convex mirror has a focal length. So this one's going to be a little bit different because the convex part, this is a negative 10 centimeters this time, produces an image of an object. Okay, produces an image of an object located 20 centimeters. So the object distance is 20. Yeah, determine the image distance here. So looking for DI again. What's its magnification? Is it real or virtual? So they give us the DO. Kind of weird wording up here, but I see here it says determine the image distance. So this must be the object distance. Okay, object distance is always positive. So I'm going to go 1 over F. So I'm going to go 1 over DI plus 1 over DO. Okay. I'm going to rearrange for DI again. 1 over DI is equal to 1 over F minus 1 over DO. This is 1 over negative 10 minus 1 over 20. I'm going to do the math on this one. Oops. 1 over negative 10 minus 1 over 20. We get negative 3 over 20 as a fraction. I'm going to solve, I'm going to flip this over. So I'm going to take this and flip it over and get DI by itself. So this ends up being negative 20 over 3, which, because we're in physics, we like decimals more than fractions. This ends up being negative 6 point, and we have 3 sig here, 6.67 centimeters. Now we've got a negative here. So this is a virtual image because of the negative part. Okay, so we have this nice little virtual image. What else do we need to figure out here? We got the image distance, which is here, the negative 6.67. We need the magnification. So the magnification is negative DI over DO. I'm using this part of the formula because I don't know the height of the image, but so I'm just going to use this piece. So negative 6.67 centimeters divided by the DO, which is 20. But this is negative, negative, sorry, my bad. So there should be another negative here. Take this and divide it by 20. And I get, I guess I can do this as a fraction in this case. I get 1/3. So this is telling me that this is diminished. It's less than 1. And it's also erect because it's a positive number. Right? I'm just going to put some little explanations there. I think that's all we needed to figure out. Cool. Try another one here. At any point, remember, you can pause these and try them yourself. We got a height of an object, and that's always positive. It's placed 2 centimeters in front of a concave mirror, so that's just telling me that this is a positive 2 centimeters. Concave mirror. So what I know about that is that this is a positive number, but I don't know anything else other than it's positive. They tell me the magnification is -4. There's a negative here in front of it. Where does the image form, and what is the focal length of this mirror? It's a tricky question. Doesn't think I have enough information to do that. Because to find the focal length, I need both the DO and the DI. The problem is I don't know the DI. So maybe I can use this information here to solve. Oh yeah, okay, this is a good one. I can do this. So what I know is the magnification part. So I know the magnification, which is negative DI over DO. So maybe I can use that information to solve for DI. So let's solve for DI first. I'm going to times up the DO part. Maybe move the negative to the other side. So my DI is going to be -4 times 2. Negative, negative, positive. So my DI is 8. Okay. So my DI is 8. So now I can use that DI up in this formula up here to find out my F. So 2, 1 over 8. Everything's positive there, yeah. Okay, so a half plus 1 over 8. I can do a math after enter situation on that one again. So my focal length is going to be 8 over 5, so I'm going to flip that over. So I get 1.6. Everything was in centimeters, so 1.6 centimeters. Okay, so I know the focal length. It ended up being positive, which is awesome. So that tells us that it's concave already. So we didn't have to worry about telling me it was concave. Where does the image form, which we found out already, is at 8 centimeters. What we know about this is because it's positive, it is a real image. I'm just going to write that there just in case. We know it's inverted because the magnification was negative. I think we're good. And this ended up being positive, so because this is positive, this is concave. But they already told us that up there, over the question mark. Okay, let's try this one out here. For a concave mirror, determine the image characteristics when an object is located 2 times the focal length. I'm thinking about that right now. I kind of already know what the answers are because of that 2f there, but let's just let's figure this out. So it's a concave mirror, so I know that this is going to be a positive number. I don't know exactly what it is. Determine the characteristics now. So I know that the object distance is positive 2 times whatever this f is. I'm looking for how does that compare to my di. So I'm going to go 1 over f is equal to 1 over di plus 1 over do. And we're looking for 1 over di here. So I'm just going to rearrange this. Okay, so 1 over f, I don't know what that is. I do know what do is. Do is 2f's. Looking pretty good. And what I'm going to do is I'm going to use a little bit of my math knowledge here to simplify this down. So I want a common denominator of 2f. So I'm going to times this side by 2 on both sides. And you get 2 minus 1 on the top. Okay, 2 minus 1, that's a 1 on the top. We got 2f on the bottom. 1 over di. 1 over di is equal to 1 over, okay, so di is equal to 2f. Oh, ended up being positive, so this is a real image because it's a positive number. Because it's positive because f is positive. If f is positive, 2 times f is going to be a positive number, which is good. It ends up being the exact same position as the do, which makes sense because we did this before. Here's my app here again. So I put this on 2 times the focal length. So here's my focal length, 2 times, that's the center. Oh, it just ends up being the same height. So if I do my magnification now, which is negative di over do, negative di, which is negative 2f, divided by do, which is 2f, it ends up being negative 1. So this is telling me a few things too. This is telling me it's inverted. There is no magnification. Right? Everything's just the same size. What else do we need to know? We have the position. That's the 2f. We have the type. It's real. It's inverted, and there's no magnification factor, which is just negative 1 actually. There we go. Looking pretty good. Okay. One more question here, and then we got refraction next week. We also have a lab this week as well. We're going to try my best to get this lab to work. I'm going to show you what a real image looks like in real life. It's a bit tricky. Hopefully my camera can record in darkness a little bit nicer than other cameras. Let's just figure out what we have. We want to find out what is the focal length of this camera. Oh, we got a concave mirror. So what I know the focal length is going to be a positive number. I just don't know what positive number it is. They tell me the height of the object, which is 4 centimeters. They tell me the distance of the object, which is 10 centimeters. If the image is erect, so they're telling me that my magnification is positive. They're also telling me my HI is positive. Okay. If it's virtual, so they're telling me that my DI is negative, but I don't know the number. And the the HI is 5 centimeters high, but they're not telling me about the sign, the plus or minus. I'll have to deal with that later on. What is the focal length of this mirror? So they give us a lot of information about the signs, but they don't tell us too much about the numbers. So let's just look at some of the formulas here. So 1 over F is equal to 1 over do plus 1 over die. So I know this part, 1 over 10. But what's this DI? I know it's a negative number. Okay, so let's, okay, so I got the HI and the HO. So if I have the HI and the HO, then I could find out the height. I could find out the height of the distance of the image, actually. So I don't need to know this part here. Get rid of this. Okay. Actually, maybe I'll use that. I'll find the M first. What's the magnification? So HI over HO. There's no negative on this side of the formula with the HI and the HO. So HI, they tell us 4 centimeters. It's positive. Nope, sorry, that's the other way around. HO, they tell us is positive 4 centimeters. HI, they tell us it's 5 centimeters. But they don't tell us positive or negative, but they do tell us that the object is erect, so the magnification must be a positive number. So for this to be a positive number, the 5 has to be a positive as well. Okay, so my magnification is 1.25. Nice positive number. Okay. Now we're going to use that as 1.25 with a negative die over do formula. And we know the do parts, so put it all 10 centimeters in there. We're going to rearrange this for DI. So I'm going to times the 10 up to the other side. And then move the negative over. Okay, so that's good. DI ended up being negative. So this is virtual. So that confirmed one thing they told us already. So they tell us that the DI is negative, so that's good. And then the last part we need to find is what is my focal length. So we got 1 over F is equal to 1 over 10 plus 1 over negative 12.5. Okay, so punch in your calculator, 1 over 10. 1 over negative 12.5. Cool. Oh, math enter. So what do we get? 1 over 50. So 1 over F is equal to 1 over 50. So F is equal to 50. You notice that this ends up being a positive number. So because it's positive, oh, so sorry, it's also all in centimeters because everything else is in centimeters. Because it's positive, this is a concave mirror, which is confirmed by what it says in the question. I don't think I actually had to tell you. You could actually determine that on your own. That's concave. There you go. Looking pretty good. All right, so this ends off this week's lesson. So I want you to work on the lab. We're going to look through the lab as well, if I can get it to work, hopefully, and do the questions in the assignment as well. There won't be that many because it's just going to deal with the math of these lenses. So it'll be a few, like 3 or 4 questions on that. And the next week, we're going to talk about refraction and how light bends when it enters into materials rather than reflecting off of materials. And I'll see you then. Bye.